In this module, we will learn how to compute vector resultants in 2 dimensions using what I'll call the sacred method. And I'll note that this is the culmination of the topic D1. So ultimately, everything that we have done before is meant to do this last main skill. And this will be the focus of the mastery test for this topic D1. So again, let's suppose we have 2 vectors A and B. And let's abstractly suppose they are both written with their components I and j. We can add them together, very much like traditional algebra. A plus b is the sum of the A vector with its components plus the B vector with its components. And initially, of course, I have, each vector has I and j, so I'll put blue for I and green for j. But also, I think you understand about rearranging the terms by addition. I can now regroup all the terms so that I have everything with I in one term and everything with j in the other term. And so therefore, I can have the resultant also in its I and j components. Graphically, this says draw A and B with its components, and the resultant vector R is ultimately drawn such that the total x component is the sum of the initial x components, and the total y component is the sum of the initial y components. So here's an example. Let's suppose I gave you a vector which has a length of 6 inches, and it's given by a slope information of 3 to 7, and I give you another vector which has a length of 8 inches, and it's given by an angle of 60 degrees relative to a horizontal axis. Okay, we want to figure out what would be the resultant of these 2 vectors expressed in I and j form, and then in terms of magnitude and angle relative to the x-axis. So let's see what we do. And we'll again use this thing called sacred, okay? The first letter being S, we're going to symbolize and separate the vectors. And my point here is that it's a good practice, even though we have numbers given, to give a label or a name or a symbol for each vector so that we can talk about them in a precise manner. So I'll call the first vector A, the second vector B. And then here it turned out the way I gave you the vectors, they already were separated, but I'll just emphasize that at this level of the course, until you become a master at this, I want to look at each vector separately so that we can go step by step. Okay, so the second A is for axis. We're going to attach the system of axes. And notice the axes go in each case to the base of the vector, not at the arrowhead, at the base of the vector. That will be this next step of how we define the axes for each vector. And of course, the unit vectors, I and j, are the same in both cases because we're using the same axes in both cases, and that we need to do to be consistent. So the third step, C is for components. We're going to calculate the components of each vector. Now, I will not do this in full detail. I'll just mention that this is now exactly the same method that we learned in the previous 2 modules about using either angular or slope information. And it's again a great time for you to practice your trigonometry skills. So I won't do all the details here, but I'll point out a few things. First of all, notice that the reference line of the 60-degree angle is parallel to the x-axis. And so therefore, we now can interpret 60 degrees as also the angle of that vector from the x-axis. That might sound obvious, but there's a trigonometric law or a geometric law that tells you that. And then following the procedure of modules 2.4 and 2.5, I'll have you verify that the A vector is negative 5.515 in the I direction plus 2.364 in the j direction, and my unit is inches, so I'll put inches multiplying everything. And the B vector is 4 in the I direction plus 6.928 in the j direction. And because I'm using 3 decimals in this case as my approximation, I wrote 4 as 4.000. Now, again, you should verify these as an exercise, and to help you prepare for the mastery test, could you do this in 10 minutes, for example? Because that would be about half of the time you have for that test. And so I'll challenge you to try and do this part in about 10 minutes. Now for the resultant, the next step is R. R is for resultant. I'm going to take the A and B vectors as I had written them in the previous slide with their components. I'm now going to add them component by component. Notice that negative 5.515 plus 4 is negative 1.515 I direction. And then in the J direction, I have 2.364 plus 6.928, giving 9.292 J, and everything again is multiplied by inches. So let's move to the next step. E is for express. Express the answer in the appropriate form. Now, the resultant that we have already is given in Cartesian form with I and J. That was the first part of our question. So we have already answered the first part of the question. But the second part of the question said express the answer in terms of its magnitude and angle relative to the x-axis. So in order to do that, I drew a picture on the right that represents the resultant vector. And the first thing I'll do is I'll say, let's make sure we see where the components go. And again, notice that I write only positive 1.515 in the horizontal component, because that component, if you see it, is pointed to the left. And the resultant magnitude, if you look at that triangle, again, we use the Pythagorean theorem, and you can verify my answer is 9.415 inches. And so now I have a diagram of the resultant in terms of all of its components and the magnitude. So that's now a next step to that second form of the answer. Finally, we need to get an angle. And here I'll say that if we use standard form, the tangent of theta is defined as the y component divided by the x component. So I'm going to take 9.292 and divide it by negative 1.515, because those were the values of the given components. And if I do that calculation, I get negative 6.133. Now, if you take inverse tangent in your calculator, you'll find negative 80.74 degrees. And most calculators are programmed to give inverse trigonometric forms with an angle between negative 90 and 90. So that's not quite the answer we want here, because I want to measure my vector from the x-axis. So in this case, I'll just have you see that we can do an adjustment by adding 180 degrees, and that 99.26 degrees is now the answer that I want. And I'll have you, for your own verification purposes, think about in that diagram, where would you have seen 80.74? I think you can see it, but I'll just leave that one detail for you to verify, okay? Now, alternatively, we could use another method, which I'll say is more directly using trigonometry, meaning by your own analysis. So let's say you define an angle called alpha in that triangle. And I could say, for example, in this case, the tangent of alpha is positive 1.515 divided by 9.292. And I get 0.6130 by approximation for this. If I do the inverse tangent, I get 9.26 degrees. And that's a great step, but not yet quite the final form. I still want to remind you that we have to give the angle relative to the x-axis. So in this case, I'm going to add 90 degrees, and you'll see that I still get the same angle, 99.26 degrees. And so notice here I'm adding 90. In the last question, I was adding 180. Don't just memorize a final addition. Just think about what each case is asking you to do. And in this case, I think it's clear that the alpha being measured from the y-axis is 90 degrees away from the x-axis plus the additional 9.26 degrees that you calculated. So the final step, D, is for draw, interpret, and reflect. We're now going to draw what I call the vector polygon of this problem, and we're going to interpret it and ask if it makes sense. So back to square one. Vector resultant is always understood graphically by adding head to tail or tip to base the vectors. So I had my blue vectors given. I'm now putting them in the head to tail format in this diagram. And the resultant, illustrated in green, is the vector that goes from the very beginning to the very end. That's the resultant vector. And we now know numbers. We know, for example, that the first vector was given to have a magnitude of 8, and we computed those components of 4 and 6.928. The other given vector was given to have a magnitude of 6, and we computed the components 5.515 and 2.364. And then we computed the resultant vector, both with its magnitude of 9.415 and its components of 1.515 and 9.292. So that would be what I would call a final diagram. Notice it's also drawn to scale. If you do this by hand, I would have you do it to approximate scale. And I'll ask you to do a couple of interpretive things. So for example, look at this diagram. Does the answer make sense? And maybe one thing you could say is, well, the resultant vector looks a little bit longer than the vector b. This is because the resultant vector is a length of 9.415, and that was a little bit longer than the 8 of the vector b. So it should be in my diagram that the resultant vector is somewhat longer, but not 2 or 3 or 4 or 5 times longer, just a little bit longer than the vector of 8. Another thing you could say is that the resultant vector points upward because the initial vectors added in the vertical direction, but it also points a little bit to the left because the horizontal components of the initial vectors almost canceled out. We had in the initial vectors 4 going to the right, but 5.515 going to the left. And so all of these things are ways of interpreting our final answers. And I'll have you ask yourself, what else could you say to explain or to interpret or to verify your answers? And in summary, what do we mean by the sacred method? It's a memory device of the step-by-step process that we took. S, symbolize each vector and draw each vector separately. A, establish consistent axes at the base of each vector. C, resolve each vector into components relative to the established axes. R, calculate the resultant by adding the like components, meaning the I plus the I and the J plus the J. E, express the resultant in the required form. And finally, D, draw the vector polygon to approximate scale and then reflect on your answer and give any other interpretations.